Borosil is India's leading scientific glassware company for the last 5 decades. We have been serving the needs of the R&D, pharmaceutical, health and education sectors in India and across the world successfully for the last 50 years. In this context, we have developed a number of products and innovations that have advanced the needs of which have catered to the needs of the scientific community. The Mansingh Survismeter, which has been developed by Dr. Mansingh, is one such product. This product is able to offer various benefits to any laboratory student, including measurement of surface tension, viscosity, interfacial tension, wetting coefficient, and other parameters like frequohesity. This product also helps save a lot of resources in the laboratory and enhances usage of time. Borosil is proud to be associated with this particular product and proud to be associated with Dr. Mansingh, who has developed this product, because we need to promote innovation. Dr. Mansingh is a luminary in his field and he has developed this wonderful product, and I really wish him all the best to continue the spirit of innovation and the spirit of thought leadership so that we can get many such more wonderful products from him in the future.
Borosil Mansingh Survismeter. Till now, the determination of liquid properties such as surface tension, viscosity, interfacial tension, contact angle, wetting coefficient, and frequohesity are being measured with separate instruments. All these properties of the same test solution are to be measured. Then, it's a time-consuming process, and the liquid or test solution getting oxidized and wasted. Borosil Mansingh Survismeter, a Singapore government patent and calibrated by NPL India, commercialized by Borosil Glass Works Limited, is a state-of-the-art instrument for simultaneously determination of surface tension, viscosity, interfacial tension, contact angle, wetting coefficient, and frequohesity of solutions. The Survismeter works on theory of selection rule, being operated at its wisdom bulb, noted as CPU, that is Controlled Pressure Unit, with new principle of R4M4, that is reduce, reuse, recycle, redesign, multi-purpose, multidimensional, multifaceted, multi-tracking of materials and methods, saving up to 90% resources, time, and can enhance the accuracy and precision associated with the measurements. The Survismeter reduces multi-step process to few fundamental steps as compared to separate measurements. This instrument is completely jacketed, thereby reducing the chances of air contamination and slippage of volatile organic compounds to the environment. Its specially designed polyacrylic chamber helps to carry out study of the physiochemical properties over a wide temperature range from 0 to 80 degrees Celsius. Survismeter finds its major application in the thrust areas of research: dyes, surfactants, emulsion, nanoparticles, polymers, and biological molecules like proteins, DNA, polysaccharides, lipids, amino acids, and nucleic acids, where it can be used to determine the critical micelle concentration and size of the micelles. The solvodynamic particle size of nanoparticles dispersed in a dispersing medium under average molecular weight of polymers. The major areas are nanoemulsions, testing fortified food items, rheology, magnetorheological fluids, that is MRF, colloids, cutting oils, protein unfolding, intercalation of DNA, pesticides, sprayants, inks, soaps, detergents, digital inks, and textile industries. The Survismeter is an indigenous technology most effective used by researchers to undertaking research activities in the areas of solution chemistry, molecular and ionic interaction prevailing in solution, protein unfolding at variable pH and temperatures. Sample feeling in Survismeter. To begin with the sample feeling, take the Survismeter unit out of the transparent polyacrylic sheet made water bath and hold the unit in hands carefully from the reservoir limb at 45-degree angle to avoid micro air bubble trapping inside the reservoir bulb. Now slowly fill the reservoir bulb to the mark by allowing the sample from a beaker, just touching the reservoir limb. Sample filling in this way reduces the chances of air contamination and trapping of air due to froth formation in case the sample solution is of surfactant or protein. After properly filling the sample, place the service meter unit inside the polyacrylic water bath and place the suction plate over the unit to hold it at 90-degree angle. Measurement of surface tension. After taking the sample in reservoir bulb, close the pressure limb and the viscosity limb with the operational stoppers. Place the L-shaped glass adapter of the syringe pump over the surface tension limb and close it airtightly. Now pull the plunger of the syringe pump slowly and you will see the sample getting into the control pressure unit. Continue pulling the plunger and you will observe that the sample starts to fill into the surface tension unit. Pulling the plunger slowly helps in maintaining homogeneous pressure inside the service meter unit and maintains uniform pressure distribution among the constituents of the liquid sample. The surface tension limb contains two bulbs. The lower bulb is the functional bulb and the upper one is the buffer bulb. Fill the surface tension limb till the buffer bulb is half filled.
The role of the buffer bulb is to give the user an extra time to start the analysis.
This also gives the constituents of the sample to achieve equilibrium, since extra pressure was used to lift the sample in the surface tension limb, thereby increasing the overall kinetic energy of the system. This matters a lot when the sample is protein or surfactant solution, and this buffer zone helps the constituents to attain the same energy state where they were before the start of the analysis. After the attainment of equilibrium, open the glass adapter of the syringe from the surface tension limb. To start the drop formation, open the operational stopper from the pressure limb. When the sample solution crosses the upper mark located between the functional bulb and the buffer bulb of the surface tension limb, start counting the number of pendant drops formed using the pendant drop counter. The drop formation is because the flow of the sample is stopped in the midway and the sample falls in the form of drop when the weight of the drop crosses the tension on the air-liquid interface of the sample. Stop the drop counting once the sample crosses the lower mark located below the functional bulb. Repeat the experiment without taking out the sample from the reservoir bulb to find out the repeatability associated with the experiment. For surface tension calculation, in addition to the number of drops formed for the sample solution, between the upper and lower mark, the number of drops formed between the upper and lower mark of the surface tension limb for a reference liquid is also required at the experimental temperature. The solvent in which the sample solution is prepared is generally selected as the reference liquid. For the surface tension limb, at a given temperature, the number of pendant drops formed for a particular reference liquid will always be constant, and hence with every sample there is no need to find the number of pendant drops formed for the reference liquid, as it can be taken from previous experiment at that temperature. For example, suppose the experimental temperature is 25 degrees Celsius and the sample is 0.1% weight by weight aqueous solution of any water-soluble protein. The reference liquid will be water. The number of pendant drops formed for water can be taken from any previous experiments where number of drops was counted for water at 25 degrees Celsius. Now, to calculate the surface tension of the sample, the pendant drop number of the sample and the reference liquid are now used in the formula as measurement of viscosity. After taking the sample in the reservoir bulb, close the pressure limb and the surface tension limb with the operational stoppers. Place the glass adapter of the syringe pump over the viscosity limb and close it airtightly. Now pull the plunger of the syringe pump slowly and you will see the sample getting into the controlled pressure unit and the bifurcating into the viscosity limb. Continue pulling the plunger and you will observe that the sample starts to fill into the viscosity unit without going to the surface tension limb. Pulling the plunger slowly helps in maintaining homogeneous pressure inside the servicemeter unit and maintains uniform pressure distribution among the constituents of the liquid sample. The viscosity limb contains two bulbs. The lower bulb is the functional bulb and the upper one is the buffer bulb. Fill the viscosity limb until the buffer bulb is half-filled. After the attainment of equilibrium, open the glass adapter of the syringe from the viscosity limb. The role of the buffer bulb is to give the user an extra time to start the analysis. This also gives the constituents of the sample to achieve proper orientation, since extra pressure used to lift the sample in the viscosity limb increase the overall kinetic energy of the system. This matters a lot when the sample is protein or surfactant solution, and this buffer zone helps the constituents to attain the same energy state with ordered orientation as they were before the start of the analysis. There will be no formation of viscous flow seen in the control pressure unit till now. To start the viscous flow formation, open the operational stopper from the pressure limb. The viscous flow formation is continuous because the flow of the sample is not stopped in the midway and the sample solution continuously flows due to gravity. In the viscosity limb, there are two marks, upper and lower. When the sample solution crosses the upper mark located between the functional bulb and the buffer bulb of the viscosity limb, start the digital timer and stop the timer once the sample crosses the lower mark located below the functional bulb and record the viscous flow time taken between the two marks. A clear continuous viscous flow can be seen on the walls of the control pressure unit. Stop the timer once the sample crosses the lower mark and note the flow time. Repeat the experiment again without taking out the sample from the reservoir bulb to find out the repeatability associated with the experiment. For viscosity calculation, in addition to the viscous flow time recorded for the sample solution, the viscous flow time record between the two marks of the viscosity limb for a reference liquid is also required at the experimental temperature. The solvent in which the sample solution is prepared is generally selected as the reference liquid. For the viscosity limb, at a given temperature, the viscous flow time for a particular reference liquid will always be constant, and hence with every sample there is no need to find the viscous flow time for the reference liquid, as it can be taken from previous experiment at that temperature. For example, suppose the experimental temperature is 25 degrees Celsius and the sample is 0.1% weight by weight aqueous solution of any water-soluble protein. The reference liquid will be water. The viscous flow time for water can be taken from any previous experiments where the viscous flow time was recorded for water at 25 degrees Celsius. Now, to calculate the viscosity of the sample, the viscous flow time of the sample and the reference liquid are now used in the formula as measurement of contact angle and wetting coefficient. Clean and completely dry the IFT capillary so that uninterrupted capillary action can occur. For complete cleaning and drying of the IFT capillary, acetone can be used. The IFT unit is having a graduated capillary and is used to measure the height of the capillary rise as well as for holding the high density liquid. In the reservoir bulb, take the sample whose contact angle and wetting coefficient is to be determined. The sample solution should be filled up to a level where the IFT capillary just touches the sample solution. Now, take the IFT capillary and airtight it with the operational stopper and place it inside the reservoir limb, allowing the system to reach the equilibrium temperature at which the study is to be conducted. Since the IFT capillary is airtightly closed, there will be no capillary action in the IFT unit. To start the capillary action, the operational stopper has to be removed and the digital timer should be started instantaneously. The digital timer should be stopped the moment capillary action stops. Once the operational stopper is removed, the sample solution starts to rise inside the IFT capillary due to the capillary action. Stop the digital timer once the rise in capillary stops. To calculate the contact angle and the wetting coefficient, the time of capillary rise and the height are now used in the formula as measurement of interfacial tension. Clean and completely dry the IFT capillary so that uninterrupted capillary action can occur. Mark up to the level where the IFT capillary tip reaches the reservoir bulb. Carefully take out the service meter unit and fill the reservoir bulb with the low density liquid to the level where the IFT capillary tip just touches the liquid. Now, place the service meter unit at 90-degree angle inside the polyacrylic water bath. In a clean beaker, take the high-density liquid and place the IFT capillary in it. Put the glass adapter of the syringe over the IFT capillary and slowly pull the plunger. Fill the IFT capillary to the half of the upper bulb, the buffer bulb. Once the buffer bulb is half filled, take out the glass adapter and put the operational stopper over the IFT capillary to make it airtight. Now fill the reservoir bulb with the low density liquid up to a level so that the IFT capillary just touches its surface. Once this is done, place the IFT unit over the reservoir limb and allow the systems to reach the equilibrium temperature in which the study is being conducted inside the polyacrylic water bath. Thus, now the IFT unit is having high density liquid while the reservoir bulb is having the low density liquid. Once the equilibrium is achieved, open the operational stopper and count the number of pendant drops formed for the high density liquid in the low density liquid between the upper and the lower mark. Once the pendant drops have been counted, take out the sample from the reservoir bulb and again count the number of pendant drops formed for the high density liquid, but now in air and not in the low density liquid. Now, to calculate the interfacial tension between the two immiscible liquids, the number of pendant drops of high density liquid formed in air and in the low density liquid are now used in the formula as
I know Professor Mansingh very well. He has developed a very good instrument called Survismeter, and this is useful for measuring many properties of liquids, especially surface tension and viscosity. So there used to be two instruments, algometer and a viscometer separately. Now you can use only one instrument and it gives both the properties. The sample required is also small, so you don't have to take large amount of samples. Also, many other properties can be derived from this instrument. This instrument is made in the country, and also it serves the purpose of several other instruments which were used separately for measuring these properties. We have already purchased one Survismeter, and I think it will be useful for all other institutions which are teaching chemistry in their undergraduate as well as postgraduate department.
I am working in this area, that is the solution properties, maybe of amino acids, peptides, proteins, saccharides, and then surfactants, their mixtures. So these particularly the instrument designed by this Professor Mansingh might be utilized in our studies also. Survismeter Mansingh has designed. We are using this. I have recently bought this instrument and is being installed in our lab also. As far as Mansingh Survismeter is concerned, that is simultaneously measuring few properties which were earlier, that is you have to go differently for example surface tension, viscosity, and it is something more laborious and more chemicals are used. And in this case, that is with the same sample you can measure viscosity as well as the surface tension. So that is economical as well as it is more accurate, because we are carrying out the measurements on the same sample. Otherwise you have to prepare differently the solutions. First you measure surface tension, then again prepare another solutions and measure the viscosity, and with different apparatus, so different solutions, it will create uncertainty in that also. In that regard, this is comparatively much better, that simultaneously measuring both the properties, economical as well as much more accurate. And from this we can have lot many parameters which we can derive, that is activation energy, contact angle, and we can study different types of systems also. Other property you can also measure with this. because contact angle, interfacial tension, surface tension, viscosity, that is the advantage of this. As I have said, cost as well as accuracy, both are, and it will be to the reach of many people, because sometimes it is also because the other automatic instruments, they are much more costly. So this is, if we compare the cost, this is much cheaper in comparison to that, and it can reach to many people, rather only who have enormous funds, but to the smaller labs this can, and they can have the same type of accuracy also.
This kind of equipment is unique in its own way, because as such I have not come across any such instrument which can measure the surface tension, viscosity, particle size or IFT at one point of time. So it would be a boon for any lab, whether it is a BSc lab or MSc lab, and the students working in those labs and working in the field where they need to measure the surface tension and viscosity of the liquids, or the experiments that they conduct for measuring the surface tension and the viscosity. So at one point of time they can measure both the surface tension, viscosity, particle size and IFT without the hassle of using different equipments, and without the hassle of cleaning those equipments and using them separately. So this is a very wonderful piece of invention that has come, and that too by Indian scientists, and this is going to be a very good instrument for the users working for measurement of surface tension or viscosity, and not only the students using it, but also the researchers doing PhD or MPhil, they can also make use of this equipment to the best of their ability.
Mansingh Survismeter basically is an instrument which can help us in determination of many parameters. It's not only surface tension and viscosity, it measures many other parameters besides that. Like we can calculate wetting coefficient, we can calculate surface tension, we can calculate the molecular weight also of some of the samples. So it's a two-in-one or multi. Earlier people used to do like viscosity and surface tension separately, but with this instrument we can measure multiple parameters together at stretch. This Survismeter is going to contribute a lot to the society. It has come up, it has developed in many phases of science. Initially he tried to formulate it, then he developed it, then a lot of sketches were made, then the time came when the naming of this instrument was at a crucial stage. This Survismeter is going to be a great help to the society, and it is basically it has come like it will be replacing a lot of the previous methods which were used initially in the science.
I have been used this instrument for my research work related to molecular interaction engineering of architecture such as supramolecules and especially dendrimers molecules. I have used this instrument for the determine the binding capacity of dendrimers with the foreign molecules, and I found that the data produced by the Borosil Mansingh Survismeter is a very accurate and very significant for the determining the various parameters. This instrument not only measures two parameters, only surface tension and viscosity, but also measures another parameters such as precocity, interfacial tension, wetting coefficient, surface area of molecules, activation energy of molecules, where the activation energy very important for the determining its application.
In chemistry, whenever we talk about anything, the first thing which comes to our mind is solution. So whenever we are talking about solutions, the first thing comes, what are the properties we are going to talk about in solutions. For solutions, whenever we talk about solutions, we talk about surface tension, talk about viscosity, talk about interfacial tension. So all these parameters have been measured using different instrumental techniques. But right now, in 1 square feet of area, now you can measure all these physical chemical properties through a single instrument called Survismeter, Borosil Mansingh Survismeter, and it's eco-friendly, and it actually uses R4M4 of green chemistry. It follows the path of green chemistry, and basically it follows most of the 12 principles of green chemistry, and through this we can actually relate this instrument with very sophisticated kind of instruments like DLS, because whenever we are talking about solution, we are talking about emulsions, we talk about their stability, talk about their particle size, talk about their interactions. So through this instrument we can also relate all those parts, and to that it's a very handy instrument to have in a lab.
My work is on magnetic nanomaterials and its application towards drug delivery. I have used this instrument for calculating the physicochemical properties of nanomaterial and interaction of nanomaterial with biological materials. And I have found that I have calculated these parameters with this instrument, and only one instrument is very useful for calculating so many parameters of the material. So this instrument is very useful for finding the properties of nanomaterial and biological material for the application purposes.
My research topic is biofuel, and I am working on biofuel. And as you know, in biofuels, physicochemical parameters are very important one, like surface tension, viscosity, and interfacial tension. And by a single instrument, this Mansingh Survismeter, we can calculate all these parameters by a single instrument without loss of sample. I have used it for my PhD work, and I am using it it is very economic and greener one, in which no sample, we can use sample again, and we can use this sample for other analysis also. So in my opinion, this is a very good instrument for research in biofuel, in the field of biofuel. And it is very cost effective instrument. It can be used in petrochemical industries also, and where large amount is not there for this instrument. So we can use this instrument in a very economic way and very greener and safe.
I have been actively engaged with the Borosil Mansingh Survismeter usage during my research work, and in my opinion, this wonderful innovation has just proved to be the backbone of my research, because we were time bound while carrying out our research program, and I was able to complete it well in time with proper justification and proper understanding, only because of the availability and the reliability of this instrument, the operation of which was very helpful and very easy to understand and very interesting. So because it produced reproducible measurements and gave very reliable data, and slowly it led to better understanding. And the most important thing is that its operation is very easy, and the observation, the secondary parameters which are calculated with the help, which can be calculated with the help of primary parameters, they are very informative and convincing. So thank you very much.
I'm working on physics related work, and mainly focus in physical chemistry. And when we deal with the physical chemistry, surface tension, viscosity, weighting constant, contact angle, and interfacial tensions are basic parameters. And when we use these all parameters in our research, so mainly different instruments are required for the different parameters measurement. But in the Mansingh Survismeter, all parameters we calculate together by this Survismeter only, and no electricity is required for this, so it's a cost effective.
Borosil Mansingh Survismeter, and invented by Professor Mansingh, Dean School of Chemical Science, and I proud to work and join with Professor Mansingh. This BMS instrument is most valuable for our institution and our country, because it is our Indian invention and green science.
Basically, it is having two words where SUR stands for surface related properties, or does not mean that only the surface tension, but coating itself is a surface science, adsorption itself is a surface science, and electrochemistry itself also surface science. So how the surface potential of the solid surface and the liquid surface could have some cutting edge. So this surface tensor service meter could encash that. Similarly, there's viscous properties. So viscosity has been also a very remarkable parameter which deals with the bulk properties of the molecules, and meter itself is a quantitative indicator. So for centuries, these 2 or 4 5 parameters have been measured individually separately by taking separate equipments and by following the multi-channel process. It is our own indigenous technology which is just based on R4M4. This is reduce, recycle, reuse and redesign, and similarly multi-purpose, multifaceted and multifunctional and multi-dimensional approach. So R4M4 exactly matching to the real spirit of green science and technology. So this technology, if goes to more and more users, I have seen there are in the remote areas where institutions are there, colleges are there, other things are there. Sometimes adequate fund is not available to them. Sometimes other difficulties, and they cannot import from outside because double or triple times cost is there. But this is our own indigenous technology. If probably comes forward and the government machinery takes a note of it, then I hope that this research could trigger the interest of many scientists, and those especially who are just at the verge of choosing science as a profession, as their career. Many universities has also introduced this in their syllabus curriculum. Central universities and state universities and institutions and industries, they have also now a bit tempted to use this because the resources are saved. Research takes a time. It was an idea in the beginning, and how this idea was nurtured, how this idea have been tried, how this idea have been calibrated by National Physical Laboratory, how this idea was patented by different Indian government and Singapore government, and how this idea reached to the commercial point of view for commercialization, for manufacturing, because it is a full-fledged science. So I also appreciate somewhere the gesture of the Borosil, that Borosil has come forward to take up this challenge. These days there is a big gap between the university industry joint venture, and since universities on their part they find that scientists do not have their ideas very solid and in a form where this potential could be transformed to reality. But in this context, in this regard, I appreciate the Borosil, who has understood its potential, and now because of only Borosil it is reaching to many users. I also thank my university that my university is also taking all measures to promote this equipment. I request the government of India, especially Science and Technology Department or MHRD or Industry Ministry, that if they give some subsidy, to the users, probably it's not only it's a circulation, but many scientists could be benefited by this because they have fund crunch. So because of fund crunch, they are not in position to buy this, and their research ideas, they cannot buy the equipments which are of crore and crore, but it's in only thousands. And further, if thousands is also subsidized, probably it will be less in thousands. So users will be benefited. In interest of the users, it could be very useful. Thank you very much, please.